It is my pleasure to introduce both of our first speakers. Klymko and Daan are staff members at the National Energy Research Scientific Computing Center, NERSC, at Lawrence Berkeley National Laboratory. They are both working on integrating HPC, high-performance computing, and emerging quantum computing technology. They also have vast experience beyond this, including quantum chemistry, machine learning. So I look forward to all of your questions at the end to Katie and Daan, in which we can address everything. Katie, please take it away with the first half of this presentation.
Thank you. So I'm Katie, and I'm going to be starting our discussion about what we do at NERSC and how quantum is eventually going to fit in with our priorities. And just to start, we wanted to give a little overview of what it is a supercomputer center does. And this is a picture of our current flagship supercomputing machine. So NERSC gets the National Energy Research Scientific Computing Center, and we're the Mission High Performance Computing Center for the DOE Office of Science Research. We support basic research in a number of different areas, some of which are shown on this slide. So biological environmental research, high energy physics, chemistry, basic environment, energy sciences, and everything that we do, we give people time on our machines is open science. So people need to use their hours that they get on the supercomputing machine to either publish or make publicly available whatever comes out. So we're supporting open science of interest to the Department of Energy. And we're very connected to the Office of Science and its users. So we have over 10,000 users from many different institutions, both in the US and around the world. And we work closely with DOE program managers to decide who actually gets time on our machines. And we make sure that whatever new hardware we're purchasing or efforts we're supporting are also supporting the DOE Office of Science mission, which is to support these basic energy sciences. And we, in general, get ordered 2,000 publications out a year. So from people accessing our high performance computing resources, we get a number of different publications from these users. Some are very high profile, but also just many different journals and areas are being touched by having access to our machines. And we highlight, some of the more high profile publications that come out, but we're very proud of the breadth of our scientific impact as well as the very high impact papers. And part of our goal as supporting this institution that provides high performance computing resources and supporting HPC work is to make sure that we are providing the highest quality hardware resources to our users. And that means that every 5 to 6 years, we're purchasing a new supercomputing machine, and we need to do research to understand both the needs of our users and how we can also push forward our user community to make sure that they're effectively using the newest type of classical computing hardware. So for instance, our current machine, which came online in 2020, is Perlmutter, named after one of our researchers at Berkeley Lab, Saul Perlmutter, who received the Nobel Prize in Physics. And Perlmutter has both CPU and GPU nodes, AMD Milan CPUs and A100 NVIDIA GPU nodes. And a big part of bringing this online was to push more of our users to use more GPU resources effectively. We're thinking currently about what NERSC 10 and NERSC 11 are going to look like. So in 2026 and in the 2030s, that's when we'll be purchasing our newest supercomputing resources. And we're planning with that in mind. So we have a pretty good idea of in 2026 what supercomputing resources will look like. But thinking towards the 2030s, that's where we really start thinking about something like quantum computing. How is it going to interact with what people are currently doing with supercomputing resources? And that's really the job that Daan and I have at NERSC to think about in the 2030s, how and if quantum computing resources and technologies are going to be integrated or play a large role in what we provide as a supercomputing center. And that's basically going to be the theme of our talk today. How are we thinking about answering this question? One thing I wanted to say too about this push for the newest types of hardware is that we also work with teams and users to make sure that their codes are being effectively run on our computing hardware. So NESAP is a current program we have that prepares users to make their codes run effectively on our current technology. So when we got GPUs, we helped people rewrite a bunch of different codes that such that they could effectively run on the new GPU system that we had. And we're anticipating something like this to be the case when we actually introduce quantum technologies, when and if we introduce quantum technologies into our hardware offerings that will actually work with users to help make sure that their codes and are running effectively and the right types of codes are running on quantum resources. So this is something that we work towards, as well as making sure that we have the latest and greatest hardware available for our users. So the next question that we're going to focus on is why us as a classical supercomputing center should be interested in emerging quantum technologies and what this could actually do for us. And so whenever we talk about this, we really look at a breakdown of the types of codes that are currently run on our supercomputing systems, right? So people get hours on NERSC and they're able to submit jobs for different areas of science. And this is a breakdown of the types of jobs that are currently submitted to NERSC. And if you look at the different types of jobs, you'll see that many of them, order 50%, are quantum mechanical in nature, which doesn't necessarily mean that all these types of codes will eventually be replaced by quantum algorithms, but it does mean that there's the potential, because they're quantum mechanical in nature, for them to have some quantum counterpart that could be run on quantum hardware that might be more effective and be able to solve problems that are bigger. Additionally, there are many types of algorithms, so scalable solvers, particle and cell codes, lattice QCD, that are not currently, they're not quantum mechanical in nature, but people are proposing quantum algorithms that could potentially speed up these types of algorithms if run on quantum technologies. So if we look at this, there's many algorithms that we think could be accelerated based on current research by having access to better quantum technologies. But also a very motivating question for us is what's not currently being even attempted to run on classical resources, just because there's no hope in actually finishing them because of the exponential scaling of these quantum systems. So we hope that with the advent of better quantum technologies, people will start running things that they're not even attempting to run on quantum technologies or on classical technologies currently, and that will open a whole new area of research for people and for us to provide resources for. So this is really the motivation for why us as a classical supercomputing center are interested in quantum technologies. So we've made a high-level roadmap of what we actually want to do to understand how these quantum technologies could impact our future and what we can do to help our users prepare for that future. And our real mission is to make sure that users have access to the best quantum hardware, software, algorithms, and support in the future once quantum technologies are ready. And we've done that through a variety of stages currently, and we have an idea of how we want to provide these resources and provide trainings in the future. And we started by providing classical resources for people interested in doing quantum information science research, and people simulating things classically to get an understanding of how they might run on quantum technologies. And that was in 2022, and we're still providing classical resources for people who want to do simulations of quantum systems on our current supercomputers. But now we're also focusing a lot more on working with quantum hardware companies and getting a better understanding of the current state of technologies and what you can actually do on these technologies. So we both have backgrounds in algorithm development, so looking at what types of hybrid algorithms could be effectively run, benchmarking quantum hardware, which we'll talk a little bit more about in this talk, and looking at resource analysis. How many qubits, how long do the circuits need to be to actually effectively solve problems of interest? And our hope is that to continue these efforts, we'll have a better idea in the 2030s of what the best types of quantum technologies are and what types of algorithms could actually be accelerated by having access to these technologies, and that we'll be able to effectively transition some users to solve problems of interest on quantum hardware when the time comes that it's ready to actually accelerate scientific applications. So for the outline of the rest of the talk, we're going to talk a little bit about what we know about what current applications could be accelerated by access to quantum technologies. Then we're going to talk about how we're actually evaluating the potential of different quantum technologies. And this is really through early hardware access. And we're going to talk about our collaboration with Quera Computing, which is a neutral atom hardware company. And then our efforts to actually benchmark hardware and algorithms to have an understanding of what the best are in this area. And then we're going to talk a little bit about some analysis we've done to understand how much this might all cost. So, the question of how good the quantum technologies, algorithms, and hardware are is one question, but also if we want to solve a scientifically meaningful problem, do we have an idea of how expensive it could be? Because that's relevant for actually, implementing this at a scale that many users could use it. And we have some interesting results from analysis we did there. So just to start, this is a diagram that was inspired by another Berkeley scientist, Lin, who does a lot of beautiful algorithm work. And this is sort of a pyramid of what we currently know about quantum speedup. So I think what gets a lot of people excited is, we know Shor's algorithm provides an exponential speedup for factoring numbers, and that's something that's quite far off in terms of implementing it, but we know that there's a really good speed up there, so people are excited about that possibility. Further down the line, there's unitary quantum, which really is doing quantum dynamics. So we have some evidence that this is empirically faster than what we can do classically, and this is something that people are quite excited about too. In getting access to quantum technologies, doing dynamics for useful systems is something that we think we can do quite effectively by having access to quantum hardware. And then towards the bottom of the pyramid, there's things that we think there could be quantum speedups for, but it's not as clear yet. So doing non-unitary quantum to solve things like ground state estimation, eigenvalue calculations, preparing thermal states. And then at the bottom, doing things that are really classical in nature, so solving partial differential equations or stochastic differential equations, optimization problems. And we have some understanding based on a lot of beautiful work that people have done on the classical cost and how much we think the quantum speedup might be for these systems. So at the top, it's provably expensive to do factoring. And towards the bottom, some of these classical algorithms, it might be the case that they're more effective if you use classical systems to solve them, but people are still actually looking into quantum algorithms that could have some speed up. So this is sort of what we know about algorithms. The point being here that there's a lot more work to be done, and it's useful to actually get access to quantum hardware to answer some of these questions. And that's really the theme of the next section: early access to quantum hardware. Some systems of which are shown on this slide is important to understand what applications could actually be accelerated by access to quantum technology. And so NERSC has been interested in getting broader access to quantum hardware, and our first collaboration was actually with Quera Computing, which is a neutral atom vendor located out of Boston. So it came out of some Harvard and MIT researchers, and currently it has hardware that operates in an analog mode called Aquila. So Aquila has 256 neutral atom qubits that operate in this reconfigurable two-dimensional geometry. It's the first neutral atom hardware system available through cloud access, and it's also one of the first platforms to demonstrate scalable logical qubits. So they had a big paper come out of Misha Lukin's group last year showing very good potential for error-corrected hardware available potentially in the near term, which was very exciting for a lot of people operating in this field. So currently operating in analog mode, but it's going to have digital capabilities coming later this year. So NERSC in 2023 started our first collaboration with this hardware company, and the point of the collaboration was really for us to get an understanding of how to use their hardware and what types of science applications could be accelerated by having access to this hardware, even though it's, still in the early stages. And this is a picture of the setup. And this is a picture of NERSC actually spelled out in actual neutral atoms. So this is really an experimental photo. And I'm not going to go into too many details about how this hardware works, but the basic idea is the following. So they trap rubidium atoms, and their first column of the periodic table, and how they have interactions between these atoms is they're able to excite the outer electron of rubidium from this low-lying electronic energy level to a high-lying state. So they basically puff out the atoms to this larger electronically activated state that can interact with its neighbors in a way that can lead to interesting and controllable interactions. So this is exciting atoms to the Rydberg state. So Rydberg interactions are the thing here that we're able to control and use to have the atoms interact. The other thing that they're able to control quite effectively is the geometry of the atoms, as demonstrated in this picture I showed you before. They can set up with some constraints any geometry that you're interested in, and then the distance between the atoms really dictates how they interact, and they're able to control individual atoms through interactions with laser pulses. So this reconfigurable geometry and this ability to excite atoms through laser pulses is really what's allowing them to create this interesting quantum system that can interact in ways that allow us to study systems of interest. So this is the basic setup. There's more details if you're interested available online, but this is what we've been using to study science problems of interest. And in our first year, we really focused on two science directions. One was preparing ground state phase diagrams. So this is relevant for quantum chemistry, for N-body like molecular dynamics simulations, for density functional theory, and just generally studying material systems of interest. And I'm going to talk in detail about some of the work we did to study the phase diagram for a particular system of interest. But we also have some nice work that I'll touch on briefly at the end about studying dynamics, because as I mentioned when I showed that pyramid of algorithms, studying dynamics is really something we think that it's quite hard to do classically, and that it should be much easier to do by having access to good quantum technologies. And we use that to study a particular system of interest. So to start with preparing this ground state phase diagram, why do we care about phase diagrams in general? Phase diagrams tell us how materials behave at different conditions. So this is a thing that people have looked at using many classical simulations. And this is sort of a basic picture of what you might get out by making a phase diagram for a particular material. So often you have different parameters in the system you control. So one might be temperature, shown on this axis, and one might be density, shown on the x-axis. And for a simple liquid, you might expect that at low density and high temperature, it behaves as a gas. As you go to higher density, it condenses to a liquid, and at even higher density, it acts as a solid. So this is useful for simple and more complicated materials, just understanding how the material might behave depending on the conditions of the environment. And this is something people have looked at, like I said, a lot with classical algorithms, but we looked at how we can actually do this for a classical model of interest on Aquila, this neutral atom hardware that we had access to. And we focused on computing phase diagrams for quantum materials, in particular, the Lieb lattice, which is shown right here. So this is a interesting lattice with a simple geometry. So you have 3 atoms in a unit cell with 2 non-equivalent sites. So B and C are equivalent, but they're not equivalent to A. So this is a 2-dimensional lattice, and it's been studied extensively experimentally, and it's noted for its exotic electronic band structure and some unusual properties in ferromagnetism and superconductivity and interesting topological states. So it's a model of interest. It would be useful to have an understanding of how this material behaves at different conditions. So mapping out the phase diagram. And this was work with 2 scientists from Quera, as well as an intern we had working with us, Mark, from UIUC. So to start with, we have all these great classical resources at Perlmutter. And what we did was to use tensor network simulation, specifically DMRG, to look at, for small systems, how this material actually behaved at different conditions. So the knobs we can control for this experimental system is the density. So this is the inverse of the atom spacing, and sort of this mean field background felt by atoms through laser pulses that we can control. And I have, spelled out on here some different types of phases that you can actually observe in this phase diagram. And this is what they look like if you pull out a snapshot of the phase. So we're saying, okay, if I look at this particular condition of the mean field background and the density, you can get this star phase here. And this is showing a snapshot of the system configuration, showing the density of atoms in the Rydberg state. Atoms in the Rydberg state are shown in yellow, and in the darker color is the non-excited atoms. And it takes this interesting type of pattern when you're at these conditions. And of course, when you change something like the atom spacing, you'll favor a different type of phase, and that snapshot is shown here. And the symmetric phase looks like this. So this is just showing if we change the conditions that the system is in, we'll get different phases. And these are the predominant ones that we observe in these different conditions. And again, this is done here classically to start at small system sizes, because we want to have an understanding of what we might expect from actually running the quantum experiments. So next, we actually did run the quantum experiments using access to Aquila. And I'm showing you a slightly different type of phase diagram here, where we've picked out the different phases, and we're comparing an order parameter that characterizes the different phases. And that can go from 0 to some higher number. And the higher the number is, that phase is more predominant at those conditions. But again, we're looking at the phases as a function of the inverse atom spacing and this mean field laser pulse that we're applying. And we're comparing what's run on neutral atom hardware to what's run on our classical resources, Perlmutter. And this is showing, again, in the symmetric phase, the collinear phase, and the star phase. And what you should really take from this is that Aquila, the neutral atom hardware, is actually doing a pretty good job, both qualitatively, but also quantitatively, compared to what we get off of Perlmutter currently, which is quite encouraging. And I'll show you here snapshots of what these systems actually look like again. And these are snapshots from actual neutral atom hardware. So you see the symmetric phase, the collinear phase. Again, there will be some defects because this is quantum hardware and things, aren't perfect yet, but things look quite good. And this is the star phase. And what I want to emphasize here is, again, we're comparing data from the neutral atom hardware with the classical resources, some measure of these different phases that we want to characterize. And we're really starting to push the limits of what you could actually measure on classical systems. And I'll emphasize that I think the data here is shown for 88 neutral atom qubits. And we also were able to collect data from Aquila for 133 atom systems. And we weren't actually able to converge these simulations classically when we tried to run a comparison. That's not to say that if we spent a lot of time optimizing our classical code that we couldn't eventually reach this level system, but it's saying that it's quite hard to do once you're starting to push these really, really large neutral atom systems. You won't necessarily be able to converge these codes classically, and that's what we actually observed when we were comparing these different simulations. So that was great. We showed that we could actually get quite good results for understanding ground state phase diagrams using neutral atom hardware. But we also undertook some additional projects, and I won't go into too much detail on what we did here, but I'll just say that studying dynamical problems on these systems is something we think is quite promising. And we put out 2 papers looking at something we call, or something that's known in the literature as false vacuum decay. So the basic idea is you start the system in some minimum that's not the true ground state of the system, and you watch it decay to the true ground state through different mechanisms. And this is a dynamical problem, and this is something you can set up and actually study using neutral atom hardware. We didn't actually run the experiments yet because they're kind of difficult, but we proposed a way to actually do this using neutral atom hardware, and we think this is a very promising direction as the technologies continue to evolve, that you could actually study problems of interest that haven't been able to be explored because of the difficulties of actually running these things on classical hardware. So with that, I'm going to stop sharing and let Daan take over to talk about benchmarking.
Yeah, in the second part of our talk, I'm going to talk about some work we've done around quantum benchmarking first, and then touch upon some of the resource and cost analysis work Katie mentioned in the beginning. So yeah, quantum benchmarking is in itself a pretty expensive and interesting subfield within quantum computing. And the overarching goal would be we want to compare how different algorithms behave, which one converge faster, how different hardwares compare. Here on the slide, we have a picture of the neutral atom quantum computer and a superconducting quantum computer. So these are quite different technologies that are operate according to different principles, et cetera, et cetera. So it's not always straightforward how you would actually want to do a performance comparison across platforms, across algorithms, across different scales of applications. So this is the overall topic of application or device level quantum benchmarking. So the question then is, how can we try to do this effectively? Because it's hard to keep up with the literature. If you look on arXiv, there's new algorithm papers put out there every day. But they're often not run on a standard set of examples. Every paper does their own test for an example where their algorithm might perform well. So it's often challenging to really understand how useful new algorithms are and how they compare to the state of the art. And on the same topic, hardware updates are also moving forward very quickly. New technologies are being introduced and proposed. And like I mentioned before, it's challenging to compare across platforms. So to try and make this a little bit easier, the project we've undertaken over the past year and a half or so is called HAMLib, and this is short for Hamiltonian Library. And we've collected a library of standardized quantum Hamiltonians that we think could be very useful for benchmarking both quantum algorithms and quantum hardware. And the reason that we focused on collecting and curating this data set of Hamiltonians in particular is because of one commonality we observed across qubit technologies and computational models of quantum computing, is that they often can be reduced to solving some Hamiltonian evolution problem on the quantum computer and encoding your computational problem as a qubit Hamiltonian. This reduction or this viewpoint can be very explicit. For example, when you think about adiabatic quantum computing or the analog quantum computation problems that Katie was discussing just before, but also if you think about quantum circuit, this quantum circuit model, you can take this viewpoint even though it might be more subtle. And then there's different types of encodings possible depending on the application domain, for example, chemistry or physics or optimization. And I'll go in a bit more detail over the next couple of slides here. So this is a high-level overview of the whole data set we generated. So we have split it up into multiple sublevels. On the left-hand side of the slide are two categories related to physical sciences, and then on the right-hand side to combinatorial or discrete optimization. So within the physical sciences, we have collected a data set for quantum chemistry and for quantum physics. Within quantum chemistry, we have both electronic structure problems and vibrational structure problems. And we've used different encodings here, such as the Jordan-Wigner, Bravik-Kitaev, and parity encoding for a range of different problems and molecules of interest. So this is really quite a big part of the data set, just the quantum chemistry problems on their own. Then for the physics models, condensed matter problems, we've looked at TFM models, Heisenberg models, Fermi-Hubbard and Bose-Hubbard models on a set of standardized lattices in 1D, 2D, and 3D. And then for the optimization problems, we base ourselves on the classical literature mostly. Besides some random graphs, we looked at some libraries that people in developing classical algorithms for combinatorial optimization have been using to benchmark their algorithms since many years. And we collected these data sets and we encoded them into qubit Hamiltonians using a couple of different encodings, such as the binary encoding, the gray encoding, and then one hot encoding. I think these are the three main ones we've used for combinatorial optimization. So all in all, this led us to a pretty extensive and pretty big data set of test problems you can use when comparing quantum hardwares or quantum algorithms within these spaces. So we looked at collecting problems over a wide range of problem sizes, and we sort of identified three ranges here. On the small end, from 3 to 20 qubits. These are the small problems. We think these problems can be interesting for testing on early quantum hardware that is currently available. A little bit larger, from 10 to 40, and depending on what type of simulator you use, maybe a little bit bigger. You could envision these benchmark problems to be useful for running on classical supercomputers and simulators. And then on the larger scale, this could be useful for doing some resource analysis for medium or longer term algorithms to test some quantum compilers, everything where you don't have to do a full-scale simulation of the quantum system on the classical side can be useful here. And then for each of these categories, we have a lot of problem instances on the order of thousands. So yeah, this is a pretty similar slide as before, giving a little bit more information about the specific use cases. So here, with the actual applications that we envision, we can compare different ansatz, for example, VQE or QAOA, and the optimization case on a single quantum computer, or we can compare cross quantum computers with a fixed ansatz and compare the accuracy that each device can reach. Yeah, and the simulation parts, you can play with, for example, circuit depth trade-offs in terms of Suzuki-Trotta decompositions, investigate new types of quantum eigenvalue estimation as algorithms, and then on the larger scale, like I mentioned, resource counts for larger calculations, and then benchmarking quantum compilers in terms of speed and quality of their results are use cases that we envision. So the analogy on the classical side that was kind of the inspiration for this project is that these type of data sets have been very successful in, for example, machine learning, such as image recognition, and in quantum chemistry, but then quote unquote classical quantum chemistry, such as these molecular data sets, to really drive forward algorithm development and innovation within the field. Like ImageNet, this competition kind of arguably started the deep learning revolution over a decade ago. So there's precedent for having a good standardized set of benchmarking problems to be a very useful tool for a community. So and then another motivation was to make benchmarking and comparing more accessible to people in the community by saving the researchers time in having to take all these steps. So this flowchart gives a high-level overview of all the different steps you would need to take if you want to benchmark some quantum chemistry problem with a quantum algorithm. So you first would have to collect some geometries of the problem, choose a basis set, solve Hartree-Fock, et cetera, it's like 6 or 7 different sets before you finally get at a problem that is encoded in a qubit Hamiltonian. And then only at the end, you can use this problem with your quantum algorithm to actually run your quantum computation. So we hope to take care of all this pre-processing and to save in productivity and increase productivity of researchers by not having each and every one going through these steps, and just being able to download the test file and then run their algorithm directly on it. So yeah, a few of our guiding principles we tried to follow while designing this library is that we wanted a well-spaced set of problems. So we want problems at regular intervals at 2, 4, 6, and so forth, a number of qubits. We try to include problems that were relevant for real-world applications, both on the optimization side and the chemistry side. And we wanted that all of our problems were already mapped to qubits and ready to use by the quantum scientists. And then, a few more practical details on the data set. It's mostly just the qubit Hamiltonians with some auxiliary data, but it's kept to a minimum. All files are stored as zip HDF5 files on this NERSC server. And this is, I want to stress that this is currently not a benchmarking suite. This is just a collection of test problems, and we leave the actual benchmarking to the end user so far. And if you want to have a look at the preprint that comes with this data set, that's the archive link shown on the slide. So this project was mainly done in 2023, and since then we've been thinking about how to continue it and actually move from this data set to an actual benchmarking suite. I won't say too much about this project because it's still ongoing, and there's not too much results to share yet at this time, but maybe at some later point. So in this project that we called HamPerf, we're collaborating with people at LBNL and Nicolas Salaya from industry to build off the Hamlet data set to develop a approach to quantum benchmarking that is based on fully based on this data set. And this is like the high level schematic that we're envisioning, where the Hamlet data set is central, and then we have a collection of algorithms and backends both on the quantum side and classical side to compare performance. But yeah, stay tuned for more updates on that at some later time. And then the final project that I wanted to discuss with you today is about some cost analysis that we did. So in this project, the key question that we asked ourselves is if we can estimate what the kind of the minimal cost would be to run some useful scientific problem on a future error-corrected quantum computer. So this is projecting towards hardwares that don't exist yet. And we looked here at some problems stemming from quantum physics known as the Hubbard model. What actually set this project off, inspired this project, was some earlier work along these lines where they looked at problems from quantum chemistry mainly, and they did a similar cost analysis. And they ended up with numbers that were like staggeringly large. This is like a cost estimate in the range of $5 to $20 billion just to solve one computational problem with a quantum computer, which is a lot of money. And if this projection become reality, that might be an issue for the a clear issue for the accessibility of these technologies in the future, and how useful they are. But what we found when looking at this a little bit closer is that all these problems discussed here are very relatively large scale problems. They're taken from quantum chemistry and factoring, and these are quantum algorithms that require a lot of resources. So like I mentioned, we were interested in how much it could cost to run maybe a little bit smaller problem, something that is still scientifically relevant and we think classically intractable, but significantly smaller than these problems analyzed here. So to answer that question, we looked into what it actually takes to do such a cost analysis. So you have to start from some computational problem you want to solve. So this is a high-level pipeline we considered for this analysis, and then you have to use some quantum algorithm that can actually solve your problem and map the actual resources required to solve the problem onto some set of logical quantum resources, for example, in terms of logical qubits and logical gates required, and then map that to some model of your future large-scale quantum computer, which use some error correction codes and has some underlying hardware specifications in terms of speed and physical error rates going on. And using this information, you can then get an estimate of the actual physical quantum resources this logical quantum resources translate to. And then with some cost model, we finally map this to a estimate of what the solution or this computation might actually cost. So we looked at the two-dimensional Hubbard model, as I mentioned before. This is a model from quantum physics, which models electrons interacting on a square lattice, which has L by L sides, so L square sides. And this is relevant in material science and condensed matter to model phenomena such as metal insulated transitions and superconductivity as applications to 2D materials and so forth. So we think it's a useful problem to study. And even though it's maybe a little bit more of a toy problem compared to the quantum chemistry models, it still has some unexplored physics to simulate. It's important to mention that this model has also been studied extensively with classical algorithms, and that good algorithms have been proposed, for example, based on tensor networks and quantum Monte Carlo, but that these approximations break down in certain regimes, and that in general, this solution is classically hard and would scale exponentially. And here in the inset, there is some results from a quantum Monte Carlo simulation they did in the quote-unquote easy regime, where these simulations work well. But we based this off another resource estimate that looked into what it would actually take to solve this problem on a quantum computer in a regime that we think is classically intractable. So we run this information through the pipeline, and then at the end we use the cost model, a very simple cost model. We just looked at current public pricing data from a variety of quantum cloud providers such as Microsoft Azure, IBM Quantum, and AWS Braket. And by aggregating the cost within two different types of technologies, namely superconducting quantum computers and ion trap devices, we saw that there was quite a significant difference in usage cost between the technologies. And this cost is here expressed in dollars per qubit second. So this is what it costs to use 1 qubit for 1 second. And with a superconducting quantum computer, on average, this is a couple of cents, while with ion trap devices, we've seen that the average is closer to $10 currently. So this is a few orders of magnitude different. And then we use this data to actually get some estimate of, under the current pricing models, what it would cost to run these larger scale simulations in the future. And of course, this is a huge extrapolation from where we're currently at to where we want to get it to in the future. But it gives some useful insight into what the range of the expected costs is. And we think that in the future, that estimate would only go down likely. And these were the results that we got in blue for the superconducting quantum computer and in orange for the ion trap device. And this starts at 10 to the 6, so around $1 million, while the ion trap starts at over $1 billion. So this cost estimate is much more attainable, even though it's still like very expensive for a single calculation. But we see this as much more feasible going forward. If this would be the upper bound, so to say, for what we can start to improving from, instead of $5 to $20 billion per computation, we have here an estimate of about $1 million for a quantum problem that we think is hard to solve. Yeah, and so to wrap up the talk today, a little bit more about NERSC and the environment that we're embedded in. So NERSC is the HPC center at Lawrence Berkeley National Lab, and we're not the only entity at LBNL that is interested and working on quantum computers. So we're really embedded in a very active and lively research communities and different research centers that are exploring different parts of quantum information science, such as the Quantum Systems Accelerator. There's the Phonon Next Center, which is recently starting. There's the Advanced Quantum Testbed, which is building hardware. And then there's a quantum networking testbed at ESNet at LBNL. And at the broader level of the DOE national labs, there's a even more programs going on at different DOE labs, such as Oak Ridge, Livermore, Los Alamos, and so forth. So yeah, there's really a lot of research activities going on within the DOE facilities along quantum computing. And then to focus a little bit more about LBNL, here are the NERSC folks working on quantum computing in the showing their pictures in the center, and then some of the other teams at LBNL with some of the researchers working there. So I think that was everything we had for you today. So we're happy to take some questions now.
Fantastic. Daan, Katie, thank you so much for this wonderful talk.